Hi, my name is Simon Stewart. I'm the lead of the Selenium project, and I'm here to talk to you today about dopamine-driven development. So let's begin pretty slowly. Your brain is sitting in a soup of chemicals as it's there in your skull, and those all impact on how you behave and react to the stimuli the world presents around you. Too low on one particular chemical, feel awful. Too much of another, and you become addicted to something, or you feel great. Get everything just right, and you're good. Some of the chemicals that your brain is steeping in are ones you may have heard of. Two examples are serotonin, which regulates mood, sleep, appetite, and a pile of other things. And another is oxytocin, which regulates social cognition. You may have heard of it as the love drug. It's the thing you get when you give someone a cuddle. As the title of this talk may have suggested, I'm not going to talk about either of those. No, instead, I'm here to talk to you about dopamine. Dopamine has a host of functions, but the one we're going to be looking at today is its role in pleasure and reward. Dopamine is a funny substance. It sometimes gets a bad rep. Think of a dopamine rush. You can't become addicted to dopamine itself, but your brain releases it in response to pleasurable experiences. It's a reward for doing something fun and enjoyable. Every time a response to a stimulus results in a reward, these associations become stronger through a process called long-term potentiation, and our world is filled with pleasurable experiences. What like? Well, positive social stimuli will result in the release of dopamine. And what's a positive social stimulus? Think of someone laughing at your joke, or being recognized for your good work, or a message from a loved one. Feels good, right? So eating good food, creating art, spending time with friends, all of these cause dopamine to be released. But also things on your computer, the internet can do the same. Someone likes a tweet of yours, dopamine. Someone sends a hug on Facebook, also dopamine. The positive reinforcement from other people's reactions, both online and in the real world, is why we love these things so much. But what does this talk about social stimuli and dopamine got to do with software development and testing software in particular? I don't know about you, but lots of software development can feel like a real slog. It's not particularly enjoyable to wait for a compiler, wait for a browser to do its thing and click through a site, wait for the results to be formatted, wait for Jenkins to finish running a pipeline, or your GitHub actions to finish, wait for your colleague to actually review your code. I mean, why do they even need to do that? You don't write garbage, right? Ugh. It's hardly a recipe for your brain being flooded with dopamine. No. You're more likely to be looking forward to your next coffee break. And yet, throughout the day, there are these little fleeting moments of joy and happiness, that moment when you finally understand why that tricky bug is happening, a brief flash when you realize you found a completely new way of breaking the software, or when that test you've been struggling to fix for so long finally starts working, or when a build really finally goes green. We want more of those moments, right? We want our day to be scattered with little fragments of joy. Mary Poppins really nailed it when she sang that a spoonful of sugar helps a medicine go down. She really was practically perfect in every way. So I'll put this out there. What we're seeking here is a way to bring joy back into our lives as software developers and testers. How on earth do we bring joy, or dopamine in our particular case, into the art of software development and testing? One of the key things that I've seen in the literature about how dopamine works is that the shorter the gap between an action and the reward, the stronger the connection your brain forms about the act being a good thing when the dopamine hits. At some level, this feels like it makes sense, right? Waiting for something pleasurable to happen can be awful. I mean, waiting to give a talk to hundreds of people, for example. But actually doing that talk and getting the feedback for it is amazing. Thanks for being here, folks. So one of the things that we should be looking to do is to tighten our feedback loops as much as possible, ideally from very long to instant. We should be striving to get to a world where we can make a change and know as quickly as possible that it works. That's the way we can get those little boosts of dopamine all the way through our day. There are other reasons why you might want the tightest feedback loops you can imagine, other than joy. One of those is that a fast feedback loop allows you to iterate more quickly. What a surprise. The quicker you move, the quicker you can react to what the market and your competitors are doing. that allows you to be more competitive. As I was writing this talk, Jason Gorman tweeted this. It's an excellent summary of why you might want to have fast feedback loops. It doesn't even touch on dopamine or joy. It touches on competitiveness. You know, we should be practicing dopamine-driven development though, and our goal should be getting to fast. Getting to fast. An idea so important, it's got a slide all to itself. Computers are an amazingly fast thing. Just look at these numbers from 2012, almost a decade ago. A level 1 cache reference takes 0.5 nanoseconds, not even a full nanosecond. That's incredibly quick. I mean, the main memory reference in 100 nanoseconds is 10 times faster than you can actually perceive. It's incredibly quick. So, you know, of course, this was 2012, and we made some real improvements since then. Oh no. That Selenium testing is distinctly suboptimal. It's not good at all. I mean, with these things, we've really blown the idea of dopamine-driven development out of the water, haven't we? What can we do? Well, this is some sort of story in a book. Our hero would grab their bag and ask their trusted companion, that's you, to join them on a perilous quest and go and consult the wizards of yore for some sagely advice. And lo, the wizards are out there that we can consult. There are two in particular that I like to talk to when I think of fast feedback loops and dopamine-driven development. The first is Michael Feathers, and the second is Kent Beck. To me, one of the interesting things that we've had about the ideas and tools available to us in order to do dopamine-driven development is they've been around for a long time. Kent Beck's book, XP Explained, was first published in 1999. Soon, there'll be folks graduating from university who are younger than this book. My son is younger than this book. Selenium is younger than this book. It's just terrifying. One of the things I liked in XP Explained is the idea of a shared metaphor, which is used to unify an architecture and provide naming conventions. You can see the idea poking through and expanded upon in Eric Evans' domain-driven design. The shared metaphor I'd like you to take away from this talk is that going fast leads to a more enjoyable development experience. Let's see what else the ancients have to say to us. First, let's take a quick pit stop with Michael Feathers. He wrote a book called Working Effectively with Legacy Code, which was originally published in 2004. Unusually, for such an old computer science book, it's still loaded with great ideas and strategies. One nugget that I particularly like is the idea that legacy code is just code without tests. Why do I like that? Because of feedback loops. The slowest feedback loop your code has is the one from adding a line of code to some rando on the internet filing a bug and complaining on Twitter. And that's the first you ever hear of it. Or more helpfully, when someone files a bug about a release on your bug tracker of choice. By adding tests to your software, particularly as you fix bugs, you can tighten that feedback loop. But there's a problem. Writing correct software is really hard. Even the simplest software is a fantastically complicated beast. There's the code you wrote. We know in our heart of hearts that our code contains bugs because, well, all code contains bugs. That code that you wrote runs on some language runtime. Node.js, Java, whatever your C libraries are. That runtime was created by other developers. So you know what? It's bugs too, right? And that runtime runs on top of an operating system. That's bound to be faultless, right? Right? Oh no. All software engineers know that all code is a tire fire. Well, we can console ourselves with the fact that code is running on hardware, and that's always good, right? Right? Oh no. There are many instances of bugs in CPUs and firmware. Who remembers such classics as as a CPU-specific rowhammer bug, or the venerable bug in the floating point unit of Pentium? Division is futile, you will be approximated, as some Trekkie wag said at the time. Don't get me started on networks. Frankly, the fact that anything works at all is something of a daily miracle. And bugs get everywhere. There's actually a branch of computer science to do with provably correct systems, typically dealing with highfalutin concepts such as formal methods. It's all about having software that's shown to meet some strict definition of correctness. If the assumption of the software's models are correct, then the software can be formally proved using logic and maths and other things I don't understand to also be correct. It takes a huge amount of effort to do this. I doubt anyone listening to this talk practices software development that way, or indeed has the time to do so. It follows, therefore, that no code base is correct. We have several guardrails to try and prevent bugs making it into the world, and each of these have different feedback loops that take a different amount of time to operate. Some of these guardrails include things like manual testers. Manual testers are awesome, but for the sake of this talk about dopamine-driven development, I'm not going to focus on them. Their feedback loops are slower and less urgent than those provided by our automated tests. However, if you're keen on dopamine, go and have a chat with one. It's always worthwhile. Sadly, no codebase has the right amount of tests written for it. Often there are too few. Very rarely there are too many. If we follow the advice from working effectively with legacy code, then every time we want to make a change to a part of a system that lacks tests, we should write at least one to verify that the software continues to function. Going a step further, what I like to do is to write the smallest possible test that demonstrates a particular bug is present and, ultimately, that it's been fixed. Sometimes that smallest test ends up being an enormous thing that ends up, spinning up an entire test env in Kubernetes and running the test there. But far more frequently, and more importantly for a tight feedback loop, quite often, I can write a test around a single function, method, or class. And so now we're in the fraught world of actually trying to name our tests. Unit, integration, end-to-end, smoke, fast, slow. List is endless. And everyone has their own definitions. So frustrating. So let me go back in time a little bit. Back in the day, Google used to talk about test sizes, small, medium, and large, later enormous. I know this because I wrote the blog post talking about this on their testing blog in 2010. I am, it turns out, an old man. You can tell by the grey in the beard. I prefer these terms, small, medium, large, because they're very clearly defined, whereas a unit test might mean almost anything depending on who you're talking to. So I suggest going to read the blog post. Test sizes fit into this discussion about dopamine-driven development and fast feedback loops incredibly well. Well, let's talk about fast feedback loops and writing the smallest possible test when trying to write a bug. We might want to write a large test to allow us to repeatedly run a particular scenario, narrowing things down until we can write a medium test. We might be able to repeat this process until we can write one or more small tests. Each time we shrink the size of the test, we make the feedback loop faster and more effective. We get more dopamine. Once I've written the smallest possible test, the next thing I like to do is to delete the larger test, leaving just the smaller ones in place. Why do I do this? Because those larger tests were scaffolding and used to help me track down why the bug was occurring. Just as a builder may put up scaffolding around a building as they work, once the work is complete, scaffolding should be removed. Imagine our cities if we never removed scaffolding as buildings were created. Now imagine your code bases. Of course, it's entirely possible the smallest test is actually a large test. That's fine. It's okay. But often, however, it's not. Now, if we follow this advice of working down to the small test and deleting the large ones, something weird tends to happen. We end up with a mix of tests that leads us to something that looks like the test pyramid. Now, I know it's not the world's most sophisticated model. And yes, I know there are refinements and rebuttals to this model, but you know what? Just because it's old and simple doesn't necessarily mean it's wrong. There's a lot of value to be had from the conceptual simplicity of this model. The key thing to take away from this model of the world, we can have faster feedback loops if we have lots of small tests and far fewer large tests, just because of how these things are defined. And there's another advantage before we go digging into that. We need to go back in time and remember what an ideal automated test is. An ideal automated test is one that's repeatable, reliable, and hermetic, no matter how large they happen to be. Let's take each of these in turn. A test needs to be reliable. If it's not reliable, can't trust the test. A test we can't trust is worthless. It only means something if a failure of that test means that there's a problem, and the success of that test means the problem it's designed to identify isn't there. We don't want to lengthen our feedback loops by having to track down whether this test failure was expected or unexpected. No, I want to get on with writing code. A test needs to be repeatable. When we're trying to track down a problem, or when we want to have the same level of confidence that software is functioning as intended on both the developer machine and the CI machine, it's really helpful to be able to run the same test over and over and over and over again. We don't want to lengthen our feedback loops with tedious and error-prone pre-test steps that load data into databases, flick toggles, and press various buttons in various UIs to allow us to run the test again. No, I want to get on with writing code. This tends to imply that test data setup is done as close to the test as possible, ideally within the test itself. And finally, a test needs to be hermetic. It needs to be isolated from the other tests that happen to be running at the same time, be it on the same machine or in some other machine. Things like sharing mutable data between tests is a nightmare for this kind of thing. Sadly, creating hermetic tests can be demanding, particularly as test sizes increase, but the payoff is that we can run tests in parallel. Being able to run tests in parallel allows us to take the long pole of test execution time to potentially be the time it takes to run your longest single test. Parallelism is one of the key weapons in achieving fast feedback loops. Now, the really weird thing with using parallelism to speed up tests is that total CPU time tends to increase when we run in parallel, even as wall time drops dramatically. There's another reason for wanting to write more small tests than large tests, and that's the law of averages. A small test tends to be very isolated, focusing on only a single thing at any one time. As the test size creeps up, however, you need to start interacting with more and more systems. This is even more true for using microservices. Let's imagine that each service you want to interact with has a 0.5% chance of not responding correctly. When there's only one service, that means that 0.5% of all your tests will now be flaky. But what if you have two services, each with a 0.5% chance of failing, or 3 or 4 or however many? Our flakiness rate goes up, our test reliability goes down. The compound risk of failure scoots ever up as we add more and more moving parts. This is one of the reasons why Selenium tests and end-to-end tests in general get a bad rap as being unstable or flaky. They just require more moving pieces than any other test, and a browser, the network, as well as your app, is a recipe for failure. That's why I like to suggest to teams that they minimize the number of Selenium tests they write. It's nothing to do with how good I think the software is. It's that I want them to have a fast, stable, reliable feedback loop. Now, we can attempt to mitigate the problem of flakiness by rerunning failing tests, but by doing so, we lengthen our feedback loops, and that's not good for our dopamine levels, or let's be honest, how joyful we can be. Worse, reruns mean that when something does fail, it takes even longer before we find out about it. Less speed, less joy, less dopamine. So it looks like we should be focusing our efforts on small tests where we can, right? But writing tests is boring. I'm sure we've been there. Writing some code, we found a problem, and then we span it in the test after the fact. Writing tests like that can be incredibly dull and often incredibly tedious and demanding at the same time. It's like the perfect storm of awfulness. I hate it. I'm sure you do too. The worst thing is when you find the code is so tangled that, although it'd be nice to write a small test, the only thing you can realistically do is write a medium or a large test. Horror. But the wisdom of the ancients tells us there's a way out. In 1999, the first version of XP Explained by Kent Beck was released. From XP came the concept of writing code test first. This principle led to both TDD and later BDD. Something wonderful happens when you write code test first. As a developer, you get the chance to write the APIs you wish your code had. Sometimes there's some head scratching and redos that happen, but ultimately you end up writing code that just feels nicer to other developers. Another thing that happens is that weird practices like dependency injections start to make more sense. You can spot the seams in your code. This leads to you accidentally writing code that is less tightly coupled to other parts of your system, and this makes it easier to write the tests. This loose coupling is something that makes system maintenance easier. I like to think of TDD as test-driven design rather than test-driven development. The way that the best TDDers write their code is fascinating. They write a small test, and then they run it, red bar. Then they add the simplest, not stupidest, the simplest code that could work, and they run the test again, green bar. Then another small increment added via a test, red bar, green bar. They do this quickly. The feedback loop is tight, and each time they run the test and get the test green again, they get a tiny hit of dopamine. And they do this time and time and time again. Writing tests becomes rewarding in and of itself, as well as the benefits to improving in your own designs. Done well, TDD is the ultimate form of dopamine-driven development. It's taken us a while to figure out how to do it, but even on the Selenium project, we're switching to writing more and more small tests because of this. Site feedback loop is great when you're writing a single test case, but in most projects, you need to actually run a build to be able to run the test. Change production code you're testing, and now everything that depends upon that code needs to be recompiled. How do we get dopamine from a slow build? It's hard, but if it's fast and our feedback loop is tight, voila, dopamine. Dan Bodart popularized the idea of the 10-second build. It's not just something to aim for, it's something to reach. When I'm writing unit tests in Selenium, I often get incremental build times of under 10 seconds. With the right setup, it's possible to do an entire clean build within seconds. How? For us, the secret is a build tool called Bazel, which was open sourced by Google a few years ago. I won't go into a huge amount of detail today, but the principles that it operates on are common and implemented maybe less efficiently in other build systems. The first thing to do is to realize that your build is actually a directed acyclic graph. Your binary depends on these modules depend on these source files, and these source files depend on these other modules, and so on and so on and so on. The directed bit simply means that there's this kind of one-way dependency. Acyclic means you can't have cycles in that graph. A can't depend on B if B also depends on A. Most build tools construct this kind of graph under the covers. Gradle and Maven do it by having projects within the same repo, multi-project builds. But Bazel takes us a step further. It constructs a graph of actions. An action might be compile a source file, but it could just as easily be run a test. This means that rather than having a phase where code is first compiled and once everything is compiled, tests are run, instead, tests are run as soon as their dependencies have been built. This can squash build times an awful lot. What can have an even bigger impact is if you have a build grid. For Bazel, this allows you to parallelize your build to run as many actions as you have nodes in the build grid. Gradle and other tools offer commercial tools that offer something similar. With a build grid, if someone who's using the same build grid has done a build recently, then you can just reuse what they built. As your team gets bigger, your build gets faster. It's a weird and wonderful way to work. But you don't just need a build tool to practice dopamine-driven development. You also need to architect your application to facilitate it. One pattern that makes this popular is the so-called hexagonal architecture. I've almost no idea why it's called that, but perhaps it has something to do with this diagram, which is from the paper written by Alistair Cockburn that introduced the concept. I prefer the alternative name, ports and adapters. Aslak Helsoy spoke about this at Selenium Conf in 2018, so I won't repeat everything here. Go and watch the video. The link is there on the screen. But the executive summary is that the main aim of this architecture is to decouple the application's core logic from the services it uses. For us and our quest for dopamine, this means that we can plug in fast local versions of dependencies during our smaller tests and then swap them out for larger versions for our larger tests. It helps keep our build times quick, our test times rapid, and our feedback loops tight. Of course, there are many, many ways to architect an application to support fast feedback loops, just as there are many build tools that you could use. This is just one of the patterns. I'm sure you can think of many, many more ways to do the same thing. With that out of the way, let's think about how we can put all this stuff into practice. Remember, the fastest feedback loop we can have is one where the code doesn't even compile or package if there's a problem. A squiggly red underline in your IDE or something like that. This is one of the reasons I really like to have production code and tests that verify it works in the same repo. Anytime I make a change in the production code, most of the small tests that need to be modified are instantly ones that fail to compile. Hurrah! Conversely, if I had the tests in an entirely different repo, I'd need to do a build of the production code, package it up, push it somewhere, and pull it into my test repo, and then it's so damn dull. I think I'd fall asleep. If you need to argue the case, and speed isn't enough of an argument, then remember that the test and production code are inextricably linked at runtime. They belong together. Maybe I shouldn't say that. Hang on. There we go. Starting up a browser can take a really long time. You can amortize that cost by reusing a browser instance where possible, but then you can do nasty things to the isolation of a test. There's a pragmatic choice you have to make in order to get the feedback loop fast. How often to use the same web browser? With something like Source, you might be able to go as low as once. On your desktop, perhaps all the time is the answer. And there's a more sensible reason to avoid browser-based tests. Large tests cover a lot of ground, so they give you great coverage, but when they fail, they lack precision. They'll tell you something has gone wrong, but very seldom are they able to tell you where that something was. So not only are they slower, when they fail, it takes longer to figure things out. Smaller tests give you greater precision. Am I saying don't use browser tests at all? No. Think of them as a very rich dessert. A little is wonderful. Too much makes you feel unwell. And it's not just browsers. Anytime you drag the network into it, you've introduced latency and slowed your tests down. Also, if the network isn't using the loopback device, not only is there latency, but you've also introduced a source of potential flakiness. As an example, a long time ago, I was the admin of a Linux server. It ran fine most of the time, but occasionally it would crash, seemingly for no reason at all. However, when the building it was in was quiet, the uptime even was dramatically longer. Downtime was shorter. After much investigation, I was left with the Sherlock Holmes adage. Once you eliminate the impossible, whatever remains, no matter how improbable, must be the truth. Somehow, people were causing the machine to crash. Just the very existence of people. After much investigation, it turned out the network cable we were using for this machine ran under a carpet. Don't ask why, it's a long story. I was young and foolish. As people walked across a carpet, occasionally they crushed the cable, and over time this led to very rare shorts. The kernel, seeing utter garbage coming across the wire, assumed the world was on fire and panicked. See, networks are evil things. One way to avoid this is to use a web framework that treats the HTTP request response as a function, which allows, and that makes it easy to switch in the backend. In Selenium 4, our network interception APIs are based on a simple interface, which treats each HTTP exchange as a simple function, which accepts an HTTP request and returns an HTTP response. This kind of approach is also used by frameworks such as HTTP 4K. Doing this makes it possible to skip the network and testing and attach your test to the backend services generating the HTTP directly. Don't even need a browser. Now, the first test you write is the one that describes the bug you're fixing or the feature you're implementing. Sometimes, when I don't know where to start in the system, I call this particular test Bootstrap, and I write code that tests a system that doesn't exist yet. This test will be at a high level by necessity. Like I said, the thing it's testing doesn't even exist yet. Quite often, this is a large test, and this is where I like to use page objects and similar functionality. Hey, take a look at loadable component in the Selenium support package for a handy base class for your page objects. Don't write more than one, just a single test. That first test will lead you to writing more tests, probably medium tests. There'll be more than one eventually, but for now, just write one. Nested within this medium test will probably be one or more small tests, but for now, you got it, just write one. Think of this as a depth-first search of the space of automated tests. We write one at a time because we want to get to the green bar as quickly as possible. That's where the dopamine comes from when our bar changes from red to green. And when we look back, we see a test nested inside a test, nested inside a test. I describe this as testing from the outside in, but you could think of it as a Matryoshka model of test authoring, the Russian doll model. Once you get a green bar, pop up to the test that caused you to write this one. Do you need to add another smaller case? Or are you done? Do you need to consider another aspect of the feature, bug, or story you're working on? If so, add just one test to help you explore the problem area. Get it to pass using small incremental changes. Run the test frequently. That movement from red to green is what you're looking for. And every time it does, tiny dose of dopamine. It goes without saying, but I'll say it anyway, that this implies your tests run damn fast. Eventually, that very first test you wrote, the largest of them all, will go green and more dopamine. And this is a point to stop and review the myriad of tests you've written. I know that all these tests took time to write, but as you're maintaining the code moving forward, will you still need them? Is this medium test covered by these small tests? Can you sensibly merge some of them? Be ruthless. It takes only a few minutes to write a test that will exist and need to be maintained for years to come. Each of them better count. As discussed earlier, this way of working, writing a test and then writing code to make it pass, is something ancients used to refer to as TDD. There's another important triangle to keep in mind when you're thinking about tests, and it's this one. This triangle is about how we balance priorities in software development. We have to find a balance between the three. Skew too far towards, say, speed and safety, and we might see costs spiral out of control. Similarly, if we focus on cost and safety, then we have to wave goodbye to being able to move fast. Slow and steady would be the way to go. Tests are interesting in this context. As you start writing them, they'll definitely take a hit to your speed. You'd be able to write more production code if you weren't wasting time on tests. And they're expensive things to write and maintain. But, and this is important, they're one of the few tools we have to increase the safety of each change we make. A funny thing happens as you add more tests. You start being able to move faster too. They help catch bugs before they're actually bugs. You make a change and some other test starts failing unexpectedly, and lo, they've started to help reduce cost too, because you can now fix the issue even before it's a problem. In other words, tests are like the ballast in a ship of development. They help us to stay level and focused, letting us leap across the waves of user stories with glee and speed. So we start adding more and more tests, but as we add more tests, particularly if they're large tests, we start to drag our build times down and down and down. Worse, we end up having to maintain those tests, and oh boy, some of those tests, ugh. We've all seen them, right? Tests which appear to use so many mocks you can't change anything anywhere without breaking a dozen of them, or tests that are so long and cover so much ground that the slightest perturbation in the background cosmic radiation of the universe causes them to fail. Ugh. In other words, tests also cause drag. They can slow us down and prevent us scooting forward at the kind of speed we'd like to be moving at. So we need to review and perhaps delete some tests periodically. How do we decide which ones to delete? Well, some are easy to pick. If they've never passed, delete them. If they've never run, delete them. After that, things get interesting. If a test is flaky and you've not managed to find the root cause and stabilize it, then removing it is better than having the intermittent signal. If a test is large, but the thing it's testing is well handled by smaller tests, well, favor speed. Always be thinking about the balance of cost, speed, and safety. I'm sure that many people watching this talk already know this, but small tests aren't just for back-end code. Too often, I see people write great small tests for their back-end code and then avoid using small tests for the UI or front-end part. It's just too hard. Part of that is because traditionally the back-end has been written in one language and the front-end in JavaScript. That's changing now as more developers become familiar with JavaScript, but it's still very true in a lot of places. And there are other problems to solve. One of the patterns we used to talk about a lot in the dim and distant days of 10 years ago was the MVP pattern, model, view, presenter. This makes it simple to decouple logic from the updates to the screen, which in turn makes writing small tests easier. There are other patterns lost in the murky mists of the past that you could take a look at. It's a really rich area to go and look up whole papers. When you're testing in the browser, one really neat trick, as I said, is to stub out the network using tools that allow you to replay network traffic as necessary. One of those that I quite like is Montback, and another is Serotonin. By stubbing out the network, you can write medium tests in place of large tests, and they'll run more quickly and more stably. If you're using Selenium 4, we provide some tooling to make this simpler. Take a look at the network interceptor when you next update. If this isn't a technique you've used before, then I definitely recommend looking into it. And look, I mentioned this before as well, so I'm going to fly by this side, but try practicing TDD. When you do, also try to make the changes you make to the tests as incremental as possible. The goal here is to go from the red bar to the green bar as quickly as possible. Remember, write a tiny failing test. Show it fails, make it pass. Get a little hit of dopamine every time you get a passing test. Sometimes it's really hard to do this on an existing project. So maybe practice on a greenfield project of your own, a little toy that you can get familiar with the technique and the tools. Also, look up code katas. There are small little exercises that help you practice. There's code in the Selenium project that was written 14 years ago. Some of it's even older. Even if that code took hours to write, it's been with us many, many, many times longer than that. To make matters worse, over time, you learn new things, you practice different techniques, you forget things you no longer need to remember, and unpracticed skills get rusty. That means when you go back to your code many moons later, it can look as if someone else entirely wrote it. To be honest, on a large code base, quite often someone else did write the code. Working on stale code that's hard to read and reason about is a great way to make your life miserable. No dopamine to be found here. So it's best to avoid this kind of complexity. There are things we can do to make our lives easier. The first is to always favor simplicity. That's why in Selenium, we like to encourage people to use IDs to find elements. Hopefully they're stable and meaningful. If they're not, in Selenium 4, we've introduced relative locators, which allow you to find elements on a page based on where they're rendered. It's a more human way of finding things. Elsewhere in code, it might mean keeping modules focused on doing one thing and one thing well. For me, it also means avoiding using more than one mock object per test. If I use any at all, I try not to. Martin Fowler has a blog post discussing state-based and interaction-based testing. I'm a huge fan of state-based testing. Who knows, you might be a fan of interaction-based, and that's fine. But there's more to life than the endless, satisfying loop of creating tests and making them pass. We actually need to get the software out and into production. Here are some more numbers you might find useful. Although the timings might be a little different for you, there's an important cutoff point where you lose focus and switch to another task. For me, that's about 30 seconds. Sadly, although our development loops should aim to stay under 30 seconds, the time that actually matters is how long we have to wait until we can merge our code and ship it to production. There are typically two gating factors for our throughput. The first is how fast a human being can reliably review a PR. The second is how fast our CI pipelines are. To maximize our speed and to keep the feedback loops as tight as possible, we should be aiming for the constraining factor to be people, not machines. And how do we do this? We should start by setting a goal time for our CI runs. I like to use the time of a fast PR review, which allows the results to be included in the review tool before someone has to ask for changes or accept a PR. Do the research for how long this is in your organization, but my finger in the air estimate is that 10 minutes is a good time to be aiming for. To get the length of time for a code review down, there's simple things we can do. What we should be aiming to do is to minimize the size of our PRs. I'm sure you've been there. That one line change that takes about 5 seconds to review, you know this, so you review it almost immediately. The moderately sized PR takes a few minutes to review. And you know this, so you wait until you have time to actually focus on it, and then you chew through a few of them in one go. The massive PR, however, gets either blindly accepted or the review is delayed for an incredible amount of time, as the reviewer knows that this PR will take like a mega decade to review properly. Just as with our tests, we should be aiming for small, complete changes that incrementally improve a product, rather than massive changes that land an entire feature in one go. The Agile folks talk about minimal viable products. Maybe we should be thinking in terms of a minimal viable change. And there's no denying the laws of physics. At some point, we need to parallelize in order to meet our 10-minute CI goal. So parallelize early and do as much of it as possible. Test isolation comes into play here, as does how we set up and use test data in our tests. By starting to parallelize as soon in the project lifecycle as possible, you can start to avoid problems with accidental test coupling or a lack of test hermeticity. If you can, make extensive use of build grids and distributed build caches, but only if you can be sure the build results are correct. If you can't, then choosing a build tool where you can avoid a clean step at the start of the build is vital, as it allows you to reuse artifacts from previous builds. Those cleans really knock your build time back and prevent your build tool from being able to do just an incremental build. Having said this, you should always favor a correct build over a fast one. In the Java world, the only tool I've used that does this properly is Bazel. Parallelizing large tests takes significant resources. If you have a smooth, well-rehearsed and fast deployment pipeline, you can take advantage of cloud providers to quickly spin up a test environment sufficiently large to deal with the surge in traffic hundreds of parallel tests can cause. You should also use products such as Source Labs to help parallelize slow, long-running tests that use browsers. And despite our best efforts, bugs always make it into production. This is one of the reasons why releasing often is a good thing. Not only is the path to production well understood and hopefully automated, but it means that the delta between releases is smaller. When trying to track down a problem, it's so much easier to find the cause if one thing has changed rather than 100. Intuitively, most organizations know that batching up changes is painful. That's why large releases need to be signed off by so many people and go through extensive test runs and checks. It's why we try and do these large changes in quiet times, not when it's good for our teams. It's why we avoid releasing on a Friday. On a podcast I was listening to recently, Charity Majors said that Honeycomb's continuous release process allowed them to keep the size of their development team small. Her argument, which makes a lot of sense, was that as releases got bigger, they got riskier and they needed more people to work on them. That means not only are large releases riskier and slower, they're also more expensive. Besides, there's nothing like the reward of seeing a new feature or bug fix you worked on make it to production. Dopamine! Another great technique is to make use of feature flags and staged rollouts. This allows you to get a feature out into production and then monitor what happens as more and more people use it. If there's a problem, just toggle the flag as quickly as you can to disable the new code path. If everything looks good, keep going. Feature flags were a key tool behind allowing Facebook to iterate quickly. If you're interested, go and look for talks by Chuck Rossi or Girish Patangay on Gatekeeper. Finally, although it would be fun to do everything to make your software development entirely dopamine-driven, the best piece of advice is to stop and think before following any suggestions in this talk. The general principle of having fast feedback loops is a great one to follow. Nesting feedback loops, one inside the other, getting longer and longer, is great. But maybe in your team or organization or circumstances, there are good and practical reasons why you can't do that right now. That's fine. It just means you have a goal to reach for and a path to discover on how to get there. Keeping in mind how important joy is to your daily work experience and finding ways to let your development process be one that rewards you little and often is a worthy goal to keep in mind and to strive for. Even small incremental improvements applied over the course of many months can get you there. Or on the way, you'll need to talk to people and help them see why you're doing the things you're doing. It's a fun journey. So, to summarize, fast feedback loops for the win. The test pyramid is still a great model to follow, even if it's old and debunked. Reliable, repeatable, hermetic tests run really well in parallel. So, parallelize all the things. And it's good to aim for a 10-second local build and 10 minutes for CI runs. That gives people enough time to do a PR review and gives you enough time to iterate quickly when you're writing tests. And finally, parallelize all the things. Hope you've enjoyed this talk. I really appreciate your time for being here. Thank you very much and enjoy the rest of the conference. I've been Simon Stewart and you can get hold of me as SHS96C on Twitter. Take care and goodbye.